All right, so we have a couple of sections out of chapter 12 in the white book. I think it's 7 in the blue book, right? Yeah. We left off at 12:6. Yeah, cool. So you should expect this throughout mathematics. If you were going to go further and you learn new functions, pretty much right after you learn a new function, you mess with it, you add them, you subtract them, you divide them, you multiply them, just like we did with radicals. One of the last sections in that chapter will be equations with that function in it. Because, of course, one of the main things of mathematics is solving equations, right? And an equation would model something in real life, and many things in real life require radicals to model them. So a square root, anybody know what a square root looks like when you graph it? Let's try it out. If I hit something that I don't know what it looks like, I just make an XY table. Somebody help me out. What's the lowest value of X that I can use? 0. And of course, what's the square root of 0? 0. I love it. What about 1? Square root of 1 is 1. All right, so far it's great. I don't want to do 2 or 3. What's the next good number? 4. I don't have to do 2 or 3, right? Hell, I skipped a whole infinite number of numbers there. So I can skip a few more. Square root of 4. All right, I think it's enough. So yeah. So 0, 0, 1, 1, 4, 2. So a square root looks like that. And it actually looks like part of a parabola where half of it fell out. Why is it missing that bottom half? Because that would be the negative root. It's missing that negative root piece. You guys semi with me? Okay. So there are a lot of things in real life that actually follow this kind of curve. You can imagine maybe a rocket lifting off, or who knows what, ball being thrown or something. Yeah. The only thing is it's never going to come back down, so that would be kind of freaky. But normally this could be like some spacecraft leaving orbit. So it's pulling away, and then it's kind of going off. It could model that. So how in the world, the most basic equation containing a square root would just be square root of x equals 3 or something. How do you think you solve that? Square both sides. I love it. So the whole idea with equations, of course, is you do the opposite operation. So whenever you learn a function, you have to learn its opposite so that you can solve those equations. So the opposite of square root is square. So x equals 9. Cool. All right. That's not too bad. Of course, they can't all be like that. They don't get too much uglier than that. What about this here? I love it, because if you squared it right now, that would so desperately suck. I don't know if you guys realize that. If I squared this right now, I would have to FOIL this side out. The whole reason I'm squaring is to kill the radical, and the radical would not die. I did it in the middle term, wouldn't I? I get 2 times this, plus 2 times, I get 4 of these. Holy shit. Not only have I not killed my radical, I've made more of them. So, definitely, and this goes back to the discussion we had about absolute values. What do you always do with an absolute value equation? You make sure that the absolute value part is by itself. Here's the same idea. My x is stuck in here. I make sure that this piece is by itself first. So I subtract that 2. And then I square both sides. For some reason, I always get somebody who does this and then they FOIL this thing out, but the square dies right there, right? Square died. Die for our freedom. Free this thing up. And then you just got to solve that equation. That's a nice Yeah, you be careful. Plus 1. Not every answer is going to be pretty. Yeah.
What would you do if you had like another rational symbol over the top?
Oh yeah. All right, let's talk about that. We're going to build our way through that. I don't want to get there yet. One thing you do have to do, and I'm not done yet because these are very simple problems, is you do have to check this answer. Make sure it actually works. Because when you square both sides of an equation, you lose information about the sign.
Positive. Should put positive.
Yeah, so if I check this, does it work? Yes. Square root of 3 times 26 thirds minus 1 plus 2. That's 26 minus 1 is 25. Radical 25 is 5 plus 2 is 7. It checks. Thank God. Because if I had this equation, and I square both sides, don't I end up here? Wouldn't I get the same answer? Would that answer work? Can the square root of something be negative? No, so right there, it's just like an absolute value equals a negative number. I know I can stop right there. So then you say, well, Jeff, what the hell? If I see the negative, I can just say, yes, it's true. Well, if you see the negative, you can stop. You would say right here, no. No solution. But you can't always see it. So let me show you an example where you can't see it. Let's see if I can make one that works. That'd be nice. Here we go. Yeah, okay, that works. Yay. Yeah. So again, the process doesn't care that there's an x in there. It says get the square root by itself first. Right, so that's the first step. No matter what's in there, you want to get the square root by itself. And then what?
Square.
Good, so the process doesn't change. This side doesn't tell me what to do. This side, I want to get rid of that square root, so I square. Now here's where I get a lot of people, even the people that know better, they tell me this is x squared plus 1. Right? And some of you guys are like, yeah, because it is. But what do you have to do here? Foil it out. It's x minus 1, x minus 1. Right? You can't just square each piece. Exponents don't work well with subtraction. You got to FOIL that thing out. So if you FOIL that thing out, x squared minus x minus x minus 2x plus 1. So that's the biggest mistake on these problems is people make it all too easy. They forget they got to FOIL it out. They lose the middle term. Now reevaluate where you are. Forget all this crap about where it came from. What is the problem telling me I need to do to solve it? Equal to 0 because I see an x squared in there, right? Whenever I see a higher power in the x, I know I've got to get it equal to 0. And then make this motion in there. Factor, cool. Go ahead. So subtract the 4x, subtract the 1. And this is a factoring that's so damn easy, but then everybody tries to force it to do the wrong thing. GCF, always try GCF first. Right? It's not this. No. It's just an x comes out. What answers do I get? 0 and 6. You better check it. So check it. That's right. So do they both work?
Just the second one.
Yeah, just the 6 works. The 0 does not work. So what the hell, math? Why did you tell me the answer is 0? Because at this step right here, right when we subtracted 1, we're right there. Now look here, this one I can see that's a negative number, so I just stop and say no solution. If I did keep going, I would get 2 answers and neither one would check, and that would be all on me because I didn't stop where I should have. You with me? Here, if x is 0, what is this? Negative 1, so it is a negative number. Did I know that at this point? No, I didn't even know x could be a 0 was possible, right? I didn't know that. So that's why math gives me an answer that doesn't work. Because when I squared this, this was negative, now it's positive. When you square a negative number, it becomes positive. So the math is like, everything's cool. You squared everything, what the hell? That's why you got to check your answers for a radical equation. You got to make sure it's not going to make it unreal. Or just make it not work. Okay. How are we doing? Is that cool? Okay. So now finally, to Lucas's question. What the hell do you do, Mr. Get your radical by itself, if you have 2 freaking radicals in the problem?
Well, that would work, yeah. Easy.
Oh shit. So if I have 1 radical, I have to eventually square once. So if I have 2 radicals, I expect to eventually have to square twice. So, do you see how there's no way to escape? Like here, again, why would I move that 1 over? Because if I squared it right now, I'd have to FOIL this out, and I don't want to. Over there, I can't escape it. If I add the 3 over, it's still with a radical. I still have to, so I just got to FOIL it right now. I get one of the radicals by itself, and the other side's just unfortunately going to be ugly. Too bad. So when I square it right now, I cut my radicals in half, right? I always think about this like a way to run a government. Isolate your radical element and then kill it, right? So here we got radical elements all over the place. Okay, divide them and conquer. It's like warfare mathematics. You guys kind of with me?
No.
I mean, it's the best I could do.
We can move minus 3 to...
Sure, and then you have to FOIL the other side. If I put the +3 here, I still have to FOIL this side out. So it doesn't make sense to even move it. I just deal with it the way it is. I make sure I get 1 radical by itself. So that when I do square, that radical goes away. So I'll do this side. I'll do half of the work. All right, you guys do that side.
How do you do that?
What do you mean how you do that? Again, this is an application of what I keep saying. Processes don't care what's in there. What do you do? What do we do here? We FOIL. All right, go for it. Again, you don't try to think ahead. There's no need to think ahead. You just put it down and you work with what you see. I think part of that is students think you're supposed to be able to see ahead of time what you're going to get. No freaking way. You apply what you know you need to do, and then you just work with it as it is. So I know I need to FOIL this out. And FOILing does not care what's in there. It's the same process. But let's be smart about it. What's radical this times radical this?
X plus 1.
This, good. X plus 1. Remember that? I'll just get radical x plus 1 squared. They go away, I get x plus 1. So then I get minus 3 of these. Minus 3 of these is minus 6 of these. And then I get the end plus 9. So thankfully something really nice happens. And now do you see what do you see what's been happened? We killed one radical. Now I can get the other radical
Yes.
by itself. I love it. Thank you. I need that other radical by itself and kill it. Right? I've got to do it one at a time. What happens with the x's?
Nothing.
Cancel. Then I get 10 minus 6 radical x plus 1 equals negative 8.
How did they cancel?
Oh,
Yeah.
because you subtract x from both sides. Whenever you have the same thing on both sides of an equation, it just goes away. Because you would subtract it, it's gone. How do you get the radical by itself?
18 equals 6.
Yeah, so I can subtract the 10. And then finally,
Cancel minus.
divide by negative 6. I don't have the radical by itself yet. Again, what's more important right now than any part of this equation is the idea of this type of equation. You get one radical by itself, square. One side is going to be ugly. It looks ugly, but that was not hard. It was nowhere near as hard as you thought it would be. You have to admit that. You have to. That's as that is itself. Collect the middle stuff together. The last one is a number. That's not that bad. And then whatever radical's still there, you get it by itself and kill it. Right? So how do I kill it? Square both sides. So I get x plus 1 equals 9. So I get x equals 8. So I squared this bad boy twice. You better believe I got to check that damn number. Right? And that will work, because that's how I made the problem. But you might as well check it. Make sure it works. Yeah.
How did you get the 6 right there at the beginning of when you started on the formula? How did you get
So minus 3 of these, right? So if you FOIL it out, you get this times this, which is x plus 1. Minus 3 of these. Minus 3 of these. So minus 6 altogether. So I just go boom, boom, put them together, right? You should be able to, now you want to start making that factoring process quicker. You shouldn't have to write both things down. You should be able to put them together as you go. If you're not quite there yet, you can put them both down. We should start to realize that's something you could do and should do. Just to kind of make, I don't want to rewrite this whole damn equation twice, right? You put that together, bam.
How many of these are this?
A few. Yeah. Let me check real quick. Hold on, sorry. 5 through 40. Number 70. Yeah, the ones you got are easier than that. So hey, what the hell? Yeah.
What's the problem? I know this is wrong, but just move the same way.
Not the same way. Definitely not the same way. But I want to show you, I don't want you to feel bad, because that's a good suggestion, but everybody help me figure out. So here's the suggestion. Right? Salah says, Jeff, all you math people trying to make everything so hard, just add the 3, subtract this guy, get your radicals all together. Right?
They're the same.
So your government, you say, get all the radicals in one building and then kill it, destroy the building. Right? But unfortunately, they kind of leak out. So if I square this now, can I just square that piece and that piece? We know we can't do that. Because you can't. Again, what does something squared mean? What does something squared mean? So if I have a plus b squared, that's it times itself. I'm going to get a middle term. You can't distribute the square. Powers do not distribute across addition. But they definitely do distribute across multiplication. Hell yeah. That is just a squared b squared. Because when you do it, ab times ab is a squared b squared. That's easy. But when you do this times itself, I got a FOIL. And now that's even worse, right? You got radicals on top of radicals. Oh my God. That actually would work in the same amount of steps that is, but this just looks horrendous. I don't want to deal with that. You guys with me? So that's why my suggestion is get one of the radicals by itself, so when you square, it dies. Then you're left with a little bit of disgustingness on the other side, but you get your other radical by itself, kill it. All right. You know that you're going to have to square twice because you got two radicals in it. You're going to have to, yeah. I don't blame you though. That's what I would do as a student, is I would always look for, there's got to be a quicker way to do this. There's got to be a quicker way than this, yeah. Okay. So here, you guys try this one. Let me give you one not quite as gross as that.
Do you know what section this is?
It's 12.6 in the white book, 7.6 in the blue book. All right, so try that one there.
That's a plus sign or a two?
That's a plus sign in there. Yeah. My markers are dying. For my tubes. Alright, so let me try to catch up to you guys a little bit here. So I can just square it as it is. It wouldn't really do me much good to move anything over. So on this side I get
4x minus 3.
over there, if I FOIL that out, I get 4 plus 2 of these, so I get 4 of these.
Plus.
Plus, this times itself is a whole 2x minus 5. So again, you don't have to do all that in your head. I'm skipping the step. You write this thing twice. And then you just FOIL it out when you get there. Now you get your like terms together, you move everything over, you get the radical by itself. Let's see. 4 minus 5 is -1. If I add the 1, I get -2 there. Subtract the 2x, so I get 2x. Yeah. In fact, here, let me show you something. I'd really rather not get fractions. And there's really nothing wrong, honestly, with leaving a number there, because when I square it, I just got to remember to square it. But I can divide by 2. It's just that when I square both sides now, what's 2 squared? 2 squared is 4 times 2x minus 5. So I don't have to have all these ugly looking fractions running around. Yes, ma'am.
How did you get the 2x minus 2?
Here? Oh, 4 minus 5 is the -1. Add 1 to both sides. Then subtract the 2x. Right? Just moving everything to one side. Getting a radical by itself. Bless you. Here, you don't have to divide by 4. You just divide by whatever goes in. You can leave a number here. There's nothing really wrong with it as long as you don't forget to square it also on the next step. Yeah?
Why don't you divide by 4?
Because I don't want to. Yeah. Sorry.
Where did that 1 come from?
This?
Uh-huh.
Okay, so get my like terms. 4 minus 5 is -1. So then I add 1 to both sides. So I think I said this the other day, I will start skipping a few steps as I solve equations. And if you don't see where I did something, you just solve that equation later. You can see where it came from. Or ask me now, that's great. Square that. On this side, I've got to do what? FOIL it out, yeah.
Wait, did you divide by 2 before you factored? Or is that factored? I mean, squared it. Right?
No.
Before you squared it, what'd you do?
I got that.
One. Yeah.
Here,
Yeah, what'd you do right before that to get there?
so here I divided by 2, because the 2 goes in here. Then I squared both sides to kill a radical, but 2 squared is 4. Right? Because I left the 2 there. Now, for those of you who divided, didn't you have a bunch of, like, over 4, over 2, over 4, right? If I divided by 4 right now, wouldn't I have the same thing? I just would rather not. Right? Because in an equation, what do I do when I have fractions? Don't I multiply both sides by the LCD and kill it? So why introduce fractions in the first place? Right? So you are certainly, it's legal to leave something here as long as it gets squared also. And then in this step, what do I do? So over here I get
4x.
8x minus 20. So then I want to have an x squared term, so I want to get it equal to 0. So I get x squared minus 10x plus 21. And that's pretty easy to factor that. Let me put it up here. How do you factor that?
3.
Yeah, 7 and 3 is really almost the only way to deduce 21. 7 and 3, they both have to be negative to make it a negative 10. So you get x equals
3 or 7.
3 or 7. And then you check them and they actually both work. Right, but you do have to check them because one of them, maybe both of them work, maybe only one of them works, maybe neither one of them works. Right, so you have to check them and see what happens. Yeah.
How does 7 work for the second part? Do you get 14 minus 5 and the square root of 11?
So let's see, 7. If I do 7 here, I get square root of 25. And over here, I get, oh yeah, so what do you give me? 7. 14 minus 5, be careful. I see, that's a common mistake. It's not 15 minus 4, it's 14 minus 5, so it's 9.
Oh,
Yeah.
sorry.
That's all right. So it'll be 2 plus 3, that checks. Yeah.
How did you get the x minus 1 squared?
Here?
Yeah.
So I got the x minus 1 when I divided this by 2, right? So I just divided by 2 because that's the most that'll go in. So I left 2 over there, and then I squared both sides. So some of you guys on this step got half x minus 1/2. Because you divided by 4, but you don't need to divide by 4. You don't need to give yourself fractions to worry about. What would you do later anyway? You would just multiply both sides to kill it. So just don't divide by as much on this step, so you don't have to multiply later. So when there's one radical in the equation, you square once. When there's two, you're going to have to eventually square twice. So I think one last section for today. Let's see what happens here. And then a little preview of coming attractions. Now, I think I've mentioned this kind of thing before, but how many of you have never worked with imaginary or complex numbers? A few of you guys. Okay. And the name is unfortunate because the early mathematicians did not think it had to be done. And when people started trying to give it names, they said, that's just imaginary, that's not real, that's what the hell are you doing? And they're like, yeah, it is not real. It's exactly not real. It's the point. But for example, in physics, do you guys know when you have a current running through a wire, that it actually sets up a magnetic field at the same time? Have you ever heard of that idea? So whenever I have an electromagnetic wave, that it has both parts. It has an electric part and a magnetic part. Electric field and a magnetic field. So in physics, you'll have an equation where the real part is the electric field and the imaginary part is the magnetic field. So there's a very basic, there's one use of complex numbers right there, is I need that to carry both sides. Now there's a lot more to complex numbers than that, and if you remember, I think we've talked about this before, if I have this equation here, how many answers do I expect it to have total? 2. And in this case it does. You would factor this, what answers do they have? 1 and negative 1. So if I have this equation, I still expect to have 2 answers. Appropriately, it should have 2 answers. And those answers could possibly mean something. But for us right now, does this have any answers? It has no answers, right? It has no real solution. Right? No real numbers answer this thing. But if I take this 1 over and take the square root, we're just going to do plus or minus there, I get this, and we just call this guy, we give this guy a symbol, I. And in electrical engineering, it's actually J. Because, it's sort of a Sharks and Jets West Side Story thing between physicists and engineers. But you use I, I'm going to use J. But anyway, we'll use the appropriate I there. Engineers out there will just rumble later.
What's that?
This is 12.8 in the white book. And I think it's 8.1. No, 7.7 in the blue book. So I do have 2 answers. I have plus or minus I. This I thing. So what we see there is the definition of I. Square root of negative 1 is I.
So it's not 1, it's I?
Ooh.
Yes. Confusing.
Say again? We know before today, what's the square root of 16? Well, even today, this is true. What's the square root of 16?
4.
4. Square root of negative 16? Not real. Right? If you give me an answer, if you think it's 4, it's obviously not 4. 4 times 4 is not negative 16. If you think it's negative 4, Still wrong. Negative 4 times negative 4 is positive 16. Shit. They always pass the negative 1 by. But now we know, today, this is old news, olden times. I'm going to get a marker that works. Now, square root of negative 16 is 4i. I love it. Yeah.
So how we know when we put no solution, when we put for I?
All right, so here we never put no solution. We said not real. And the
That's
reason we
not
did
real.
that is because we hadn't learned about non-real numbers yet. So this is technically correct. But it's sort of like saying 3 plus 7, what's the answer? And you say, it's a real number. It's not satisfying. It's like, there's got to be a number. It's not, I got to learn about these things. So we hadn't learned about not real answers, so all I could say is it's not real. Now it can be much more specific. Well, which not real number do you mean? And again, I hate that they use the word imaginary, not real. That sucks. But it makes students believe, it verifies that, oh yeah, they're just making this shit up. Here they are being completely honest, finally. Oh yeah, by the way, guys, it's all imaginary. This is all a dream. No. It's just an unfortunate name. And it kind of makes it seem like it's harder than it really is. But the main thing to realize here is, that's a side note. But if I is the square root of negative 1, and that's what I do be, is the square root of negative 1, what's I squared?
Negative 1.
Negative 1. Neat! So the only kind of number I can square and get a negative answer is an imaginary number.
Does it apply for all even roots? Does it apply for all even roots?
Let's see. What's I cubed?
1.
Careful now. How do you do I cubed? You break it down, because I know what I squared is,
The same first one.
and I know what I is. So I'll say, okay, I cubed is I squared times I, isn't it? You guys with me? And what's I squared?
Negative.
Negative 1 times I is negative I. So I cubed is negative I. Go with me. If, and again, on one level, we know that this thing is not real. We know it doesn't make sense with what we've used before. Are you with me? But if I can, and therefore, what is this? I don't have a clue. It's even worse than not knowing. I think it's nothing. I think it doesn't even exist. Well, shit, I can call it I then. There you go. So the minute I call this I, there's ramifications of that. If I square both sides, I get I squared equals negative 1. The square root goes away. You with me? And then I can keep playing around with it. So on one level, it always feels like you people are just playing around with this shit. But on the other side, there are physical interpretations of this. There are reasons we need this. Without complex numbers, there would be so much we would not have today. There's so much in electrical engineering that relies on use of imaginary numbers. It's almost silly. We'd be basically almost in caves now if we didn't have this. We're still walking around with the candles. Good day to you, sir. For some reason, I have Ben Franklin in my brain or something with a little candle over it. So this is why I don't teach history. And how about I to the 4th?
1.
Yeah, because the best way to do that is I squared times I squared. Negative 1 times negative 1, 1. So this is kind of freaky. What's I to the 5th? It's I to the 4th times I, so it's 1 times I. It's I. It starts over again. I know. Let me see what we had working. So watch this. Let's kind of summarize what we just did. And again, anytime you make a statement like this, it must have ramifications. There must be something that comes off of this. So the first thing I can really do with this kind of statement is start playing with it. Well, what if you square it? And then, oh, we got something. What if you cube it? Oh, we got something else. What if you 4th power it? So we got I is I. That's neat. I squared is negative 1. I cubed is negative I. I to the 4th is 1. And then it starts over again, right? So this is something we call cyclic. There's a cycle to it. It keeps repeating itself, like sunspots, roughly every 11 years, right? So I to the 5th would be I again, so forth. So here's the really neat thing. Can anybody work out for me what I to the 413th power would be? Without going down this list until you hit it. Yeah. Every 4, it's 1 again. So if you get a remainder 1, that must mean you're here. Right? Or, here. If you get remainder 2, remainder 3, remainder 4, hey, you wouldn't get remainder 4 because 4 are going evenly then. So what 4 goes into 413 how many times? So this, you could rewrite this as I to the 412 times I.
How do you know?
Say again?
How do you know? 412.
How do I know what now?
412.
Because what is this cycle based on? Every 4th one, it starts over, right? Every 4th one
Divided by 4.
divided by 4. So what does 4 go into? 412. Right? So then what's I to the 412th? 1. Every 4th one it repeats. Every 4th one it recycles. So that'll be 1 times I. A much better way to do it than this. 4 goes into 413 evenly with 1 left over, so I must be here. I to the 1st. Right? So what about I to the 87th? 4 goes into 87. Some number of times with how many left over? 3 left over, right? So I must be here. That must be negative I.
Can we explain that again?
So I, and again, you can write it like this. Do you guys understand that if I kept going, I would go a little insane if I went too far. But I8, I5 is I.
1.
I6 would be negative 1. I7 would be negative I. I just kind of repeat the whole thing I just did, wouldn't I? Yeah. So I8 would be 1 again. I12 would be 1 again. I16 would be 1 again. So I84 would be 1 again. And how many I's have left over? 3. So then what's I cubed? Negative I. So I end up just having to know these, and that would be my remainder. So 4 goes into 87, 21 times, with 3 left over. So the answer must be negative I. Okay. Now, that's too much time to spend on that, because while that's interesting, the most important part of all that, and yes, you will have to do a problem like that. I will give you a problem like I to the 92 or something, right? But the most important part of all that is probably the I squared piece. And I'll show you why. So let's get a little bit more out there. We have real numbers, and we have imaginary numbers. If you put these together, you get what's called complex numbers. Right? Again, you guys are like, that's basically exactly what I call this shit. But if I have a real part and an imaginary part, that's a complex number. So, for example, if I have 5 minus 2i, that's a complex number. Where a is, what's a? 5. B is negative 2. Right? 7 plus 4i. A is 7, B is 4. What about 11? Is that complex? Hell yeah. A is 11, B is 0. So, tell me this. Do you guys remember, we talked about this a little bit before, you have the natural numbers? Remember this whole thing? 1, 2, 3. The things that came naturally to us. Then you have the whole numbers. the added zero, whole numbers. Then you have the integers, added the ideas of negatives. Then you have the rationals and the irrationals on the side, and then all this crap is real. Well, outside of there is all that, outside of there is complex. And out here would be the imaginary numbers. So, every real number is also a complex number, just with the imaginary part is just zero. That's all it is. So every single number you've ever seen in your entire life has been a complex number. It's just that the imaginary part was zero. Right? So you didn't have to worry about it. Right? It's sort of like if I said every single whole number you've ever seen in your life is also fraction. Because it's over 1. Did you ever have to worry about that over 1? No. So you wouldn't say that's a fraction. That's silly. But it is. It's a rational number. You can make a ratio out of it, right? So every single real number we've seen is also a complex number. Right? It's just got a zero imaginary part. Okay. So every complex number has to have this form to it. So what do you think you're going to do now? Now that we've talked about this new idea of complex numbers, what's the very first thing you do when you learn numbers? You learn your symbols for the numbers, and then you start to add them, subtract them, multiply them, right? Kind of makes sense. So we're almost starting back in, I don't know, kindergarten, first grade, where we first learn 1 and 2 and 3 and then symbols. But now we're doing it at this much higher level of complex numbers. So if I had, adding, subtracting is stupid easy. If I had 4 minus 7i, plus 2 plus 5i. What do you think is true here? What am I allowed to put together? Like terms. So in this case, the I acts very much like a variable. So I'm going to get 6
plus, minus 2.
2i. Cool. I like it. So what if I multiply those together? Take a minute and do that. So I, don't forget, I is not a variable, but very often it can be seen as one. You know, for example, there, it acts like a variable. It's just a thing I don't know yet. And we've seen things that act like variables before. 3 radical 7 plus 2 radical 7 is 5 radical 7. So the radical 7 acts like a variable. So I is just radical negative 1. It's going to, same thing, right? The difference is when I multiply, I remember that I is not x. I is not a variable. I squared has a value. So does I for that matter, but we don't normally want to look at it. But when I FOIL this out, what do I get? 8, 20i,
Minus 40i,
14i,
minus 35i squared.
35i squared. So I can obviously put my like terms together. But what else can I do?
Plus 1.
Negative 35 times -1.
Good. I squared is -1. So that's what I meant earlier when I said the most important part of the whole list was I squared. It's the one that happens the most. Right, when I FOIL things out, I'm going to have an I squared term. I squared is -1. So go ahead and put -1 in there. So then you get 8 plus 6i plus 35. 43 plus 6i. So it kind of makes sense. When I multiply two complex numbers, my answer should be a complex number. So it should be able to be written as a plus bi in that form. Okay. So that's not too bad. That's basically foiling with one extra step because you know what I squared is. We normally don't know what the hell x squared is. Here we know what I squared is. So go one extra step. So what about dividing? Why, Jeff, man? 3 out of 4 operations is enough. But if I wanted to divide... Oh, I thought you were... Unfortunately, you can't now suddenly start dividing the i's away and stuff. I mean, that never ever works. I don't care what kind of numbers you're looking at. Right? Division cannot cancel subtraction or addition. So what the hell? How do I do this? How did we do something like this?
Multiply by square 7 plus 2.
Good. Multiplied by the conjugate. Remember that just change the sign in there? So I multiply this by radical 7 plus 2, radical 7 plus 2, blah, blah, blah. So here, what are we going to multiply by?
The I is minus
Minus 2, because remember, I is just radical negative 1. It's going to act the same way other radicals do. So this is what I think I told you guys. We did this, and I said it was a conjugate, and I said in our near future is complex conjugates. So here the hell it is. And it's not anything more difficult. If it's 3i plus 2, I multiply by 3i minus 2. Why the hell do I do that? Because then the only place where i's could still show up, which is in the middle term, goes away. Because, of course, I made it so they'll cancel. So on the bottom, I just get 3i times 3i is 9i squared. Plus 6 minus 6, that goes away. Minus 4. And on the top, I just get 6i squared, minus 4i, minus 3i, plus 2. Right, now I can start putting my like terms together. And also replacing what with what? I squared is negative 1. Cool. So on the top, I get negative 6 minus 7i plus 2. On the bottom, I'll get negative 9 minus 4. So I get negative 4 minus 7i over negative 13. So I just replaced I squared with negative 1. So you just go one more step than I normally can, because I itself is not x. I is a number, and it's radical negative 1. So I squared, I know what it is. And then one last thing I can do here, since they're all negative, I can cancel the negatives out. Just make it look a little better. And then I can make it look, here's my a plus bi. I always have to make it look like a plus bi. If I split them up, it looks like a plus bi. It is a complex number.
No, we just know the I square, we don't worry about the 7i or anything.
Yeah, I can't. Now, be careful. I always get somebody start replacing I with negative 1. But I is square root of negative 1, which is, I can't do anything with that. So that's why I just leave it as I. Right? I don't want to look at radical negative 1. Let me just leave it I. But I squared is nice. I want to see that. That's just negative 1. I can do that. So where this is leading us is we can finally give complete answers to the question, solve the equation. There have been times when we've had to leave out answers because they were complex and we didn't know about complex numbers yet. So now every single time I have an equation, if it has a fifth power in it, and that's the highest power, I must get 5 answers. Some of them might be imaginary, complex, and some of them might be real, but there better be 5 of them total. That's kind of nice. I know exactly how many answers to expect. Before today, I didn't know how many freaking answers I would get. So some of it might not be real. I might get 1 answer, 2 answers, I don't know. Now I've definitely got to get 5. End of story.
How did we get the positive 4?
Oh, they were all negative? So I just
Taking out
Took a negative out of the top and bottom.
Okay.
Yep. Cool. So one last thing I'll show you, then we'll call it a day. It's pretty much, well, I'll let you out a little early. Why not? Let me see if you guys can handle this right now. Well, this is one you should be able to handle. How do you factor this?
X minus Y, X Y.
Because any real number, when you multiply it by itself, it's going to come out positive. So I have to have negative and plus to make it negative here, right? So why before were we not able to do this? Inherent in that question is me saying that we're able to do this now. We were not able to do this before because I needed different signs on my numbers. But then if they're real numbers, they'll always come out negative then. And I need a plus here, don't I? You guys kind of with me? I have to have different signs so the middle term dies. But then I'm forcing them to come out negative then. That's why this didn't work before. But now it'll work all day. Right? It's not that it suddenly works. So I got to be careful how I say that. It's not that it suddenly works. It's that we know how it works now. We didn't know how this worked before. So we just had to say prime can't be factored over the real numbers. But now we can factor this over the complex numbers. 4i. 4i. Right? Because if you multiply this out, what do you get? X squared plus 4ix minus 4x. The middle term goes away. Minus 4i squared, but what's I squared?
-1.
Look at me with the minus 4. I love it. 16, right?
Yeah.
I squared is negative 1, so then I get my x squared plus 16. Check. Oh, shit, yeah. In a way that's nice. I mean, hopefully some of you guys were a little irked that you can factor of sum of cubes, but you can't factor sum of squares. Where some of you guys are probably just like, well, I just can't, so I'm done. But some of you hopefully were a little like, I should be able to do that. What the hell? Yes, you can. We just didn't know the numbers that we needed to use to do them. You know, I like that. Thanks, Jeff. I feel so much better. Okay, so that was section 12.8 in the white book, section 7.7 in the blue book. So we are going to get into the quadratic equation section, and that's really why we're learning these complex numbers now, because now we'll see all the answers to a quadratic equation. Some of them might be complex. Okay.